So, hello everyone. So in this consortium, we have the goal of trying to find ways to better characterize the turbulence intensity. The turbulence, as you know, is super important for the design of the turbines, development of wind farms, and also to better understand the production of the wind farms. So my name is Julian Dajczgewand. I'm the technical solution manager for Vaisala. Basically, I'm supporting customers in terms of how the Lidar works, how to use it, but also how to use it in different applications for both wind resource assessment as well as wind farms in operation. I will present some of the outcomes we got from this project and future perspective to improve this the measurement of turbulence intensity. So quickly, for those that don't know much about Vaisala, you might have heard about Leosphere. So Leosphere, manufacturer of Lidar, was acquired by Vaisala 6 years ago. We're a global company with a broad portfolio of products, mainly focused on weather and environmental measurements, and also with the platforms that uses data from sensors, forecasts, and AI algorithms to help decision makers to take better decisions. Vaisala has more than 2,000 employees all over the world, more than 60 nationalities, and something really important, and that's why we also participate in this kind of consortium, is that we are committed to make our product the best, and that's why there's a strong investment in R&D for all product portfolios. If we look at the LiDAR technology at Vaisala, we develop and manufacture 3 types of LiDARs for different applications. I'm showing you here in this slide. The well-known WinCube vertical profiler that people were referring about in the former slides, in the former presentation, sorry. These LiDARs go from using pre-feasibility to operation of a wind farm. So the WinCube vertical profiler in both onshore and offshore configuration. Then we have the WinCube scan, which allows for long distance measurements, which is widely used for performing WRA offshore from the coast. And lastly, the WinCube nacelle that is used for checking the performance of wind turbines, as well as to perform LiDAR assisted control to improve the production of the turbines. On top of that, we have an extra layer with the software, including our recently released software called Compass, which allows to fleet management and helps combining measurements with historical data to manage the full campaign. So if we go now to the project itself, so what's the motivation behind this project? I think you all know having a more precise measurement of the turbulence intensity is one of the most important challenges when assessing the wind conditions. The turbulence intensity is used for several calculations, including load validation, turbine seating, energy yield assessment, site suitability, wake losses, and others. So clearly having a good quality measurement has a strong impact on the success of a wind farm from a financial point of view, especially. So what are the current challenges to measure turbulence with LiDARs? In some conditions, LiDARs tend to underestimate or overestimate the turbulence intensity. You saw some of these effects in the former presentation. This applies to all LiDAR manufacturers, and it's not related to the WinCube itself. It's related to the way the vertical profilers work. And so why is it so challenging? And I will go in detail in the next slides, and some of them were already mentioned before. There are different effects related to the position of the measurements, the volume of the measurements, the terrain condition, and also the sampling rate. And the objective here is to demonstrate that the new strategies to improve the turbulence intensity measurements, and also to show you some of the future perspectives. So let's take a look at some of the specifications of the WinCube that are mainly related to this project. First of all, the measurement frequency. WinCube will measure each line of sight around 1 second and move to the next line of sight. The wind field is reconstructed at 1 Hz, and the 5 line of sights are measured. The other parameter that is important to consider is the volume of measurements. All lidars will measure a certain volume, not a point, like an anemometer. In the case of WinCube, which is a pulse lidar, the volume is constant with height, which means that the spatial accuracy remains constant at all heights, as you can see in the slide. And I will go into more detail in the next slides about this feature and why these are important for this project. So if we look at the one of the sources of error is the interbeam averaging that was mentioned before. The wind field is reconstructed using the 4 line of sights that are not located at the same position, so same height but different location. In the case of a floating lidar, this effect becomes much more important. Depending on how fast the floating lidar is moving and the frequency of the motion, this effect will become much more important in some cases. And this will have an impact, of course, on the turbulence intensity on the measurements. And I will show a potential solution later. The other source of error becomes from the volume of measurement. Because of the accumulation time, when the buoy is moving, the volume of measurement will be moving. Without motion, the WinCube is measuring the same wind field, but with motion is measuring different heights and mixing different wind fields. Of course, the frequency and the amplitude of the motion will have an impact on this effect. And of course, again, depending on the type of buoy, some of the buoy moves faster than others, the impact will be higher or lower. The solutions for the interbeam, which is related to the reconstruction using the 4 laws, will be to increase the sampling rate as a potential solution. I think there was a question before in the chat about this. So the standard configuration, it's what we call the 1 Hertz. Is related to the accumulation time. This is the commercial product. The customized, let's say, version of the WinCube using this project has a reduced accumulation time. So it's spending less time in each line of sight. So the effect of the motion is less important. So you fully reconstruct the wind speed before the motion becomes important. The other effect, which was the intrabeam related to the volume of measurement, a potential solution is to reduce the volume by using shorter pulses. And there was a proposed method and test by reducing 30%, around 30%, the volume of measurement, the length of this of the probe. And this was tested, but the results were not didn't show a great impact, an improvement in the turbulence intensity. But of course, this is something we should probably look into more detail. So now we focus on this solution for increasing the sampling rate. And as one of my colleagues like to say, there is no free lunch. So this doesn't come for free. Data availability depends on several parameters. The sampling frequency, which is related to the accumulation time, will have an impact on the data availability. So we can go faster, but the faster we go, the less data we accumulate, and having less availability will have an impact on the accuracy of the measurements. So there's a right trade-off to see what's the best condition. We found that this reduction was actually a good trade-off without losing much data availability. So some of the results that we got during this campaign, we can see on the left the bias on the turbulence intensity and the deviation of the turbulence intensity. The dark blue is the standard configuration. The light blue is the fastest frequency. And you can see around 30% reduction in the biases, showing that clearly this is a good approach, which also makes sense physically, because we are fully reconstructing the wind field before the motion is having an impact on the reconstruction. And on the graph on the right, which is also quite interesting, it's the turbulence intensity mean bias error by wind speed bins. We can see that at all wind speed, there's an important reduction on the biases for the turbulence intensity. You can see in purple the standard configuration, and in pink the higher frequency. So there's also some other developments we are working on here at Vaisala to improve the turbulence intensity. It's an important topic for our customers, our partners. End of last year, one of my colleagues presented this graph I'm showing you here at ACP. This graph is showing in the dotted red lines will be the DNV recommended practice for turbulence intensity. The DNV RP is 0661. There's also another one for load assessment. The different curves that we show there are different methods that we are using to calculate the turbulence intensity. So the red curve with the dots, that will be the standard configuration, which seems to work well in general, with always a certain bias, overestimating, and at low speeds becoming more challenging. But here, what matters is actually the last development we had in the graph is presented as a javelina, which shows a really good improvement in the TI for all wind speed. And this is something we are trying to push in the future, and our scientific team is working on developing this approach. And we hope to be able to share more in the future. We have also tested other ways to improve the turbulence intensity, like using machine learning and also other methods. But this method, Javelina, which is basically compensating for the interbeam, has shown really good performances. So to conclude, I show you the sources of errors in the turbulence intensity. These are well understood, which is already, I think, a good first step. Once you understand what's happening, it's easier to try to find a solution. I also show you that decreasing the repetition rate show an improvement in the turbulence intensity measurement. This is especially important for floating lidars, for platforms that are moving. I also show you briefly some of the developments we are currently working on to improve the turbulence intensity, where we have this great candidate for the future. And lastly, I'd like to mention something that I haven't talked about during my presentation, which is about the motion compensation. This is quite important, especially for buoys with a high amplitude of motion. And in these cases, when you apply motion compensation, what is challenging and really important is the synchronization between the IMU from the inertial motion unit from the buoy and the timestamp from the measurements.